Welcome to a lesson on defining a piecewise smooth parameterization of a path in the xy plane to prepare for line integrals. One skill needed to successfully evaluate line integrals is to be able to define a smooth parameterization of a given path in the xy plane. This means you want to be able to break up a given curve and define it in terms of t so each piece is smooth while the value of t remains continuous. So let's take a look at our first example. Our curve is this 2 by 2 square, and since the square has 4 sides, we'll have a parameter for each side. So we'll label this curve 1, curve 2, curve 3, and curve 4. So for curve 1, we go from the point 0, 0 to the point 2, 0. So that's pretty straightforward. If we let x equal t and y equals 0, and then define t on the closed interval from 0 to 2, we would take the path of curve 1. Now for curve 2, we go from the point 2, 0 to the point 2, 2. Notice x is equal to 2, and y increases from 0 to 2, but we can't just put y equals t because the value of t now has to start at 2. So if we start y at t and then subtract 2, and then let t go from 2 to 4, when t is 4, y would be equal to 2, and it would take the path of curve 2. Now let's take a look at curve 3. We go from the point 2, 2 to the point 0, 2. But now t has to start at 4, and we'll see where it stops. So we need to create a formula with t in it where t starts at 4 and x goes from 2 to 0. So if we let x equal 2 minus t minus 4, let's see what that does. When t is 4, we subtract 0. That's good. When t is 5, we would subtract 1. That's good. And when t is 6, we would subtract 2. That would give us 0. So that's good. And then our equation for y would stay at y equals 2. So t is on the closed interval from 4 to 6 this time. Now for curve 4, go from the point 0, 2 to the point 0, 0. X stays at 0. We need an equation for y, but t has to start at 6. So very similar to what we did up here. Y starts at 2, and now we're going to subtract. Instead of just t, we'll have to have t minus 6. When t is 6, we'd have 2 minus 0. When t is 7, we'd have 2 minus 1, so we stop at t equals 8. So now we'll go ahead and write this curve as a vector valued function using these parameterizations. So we'll have 4 pieces. The first piece will be t comma 0. And t is on the interval from 0 to 2. Then we'll have 2 comma t minus 2 from 2 to 4. Here we're going to have 2 minus t plus 4. It's going to be 6 minus t for the x component. And then y is 2. This is from 4 to 6. And for the fourth curve of 0 comma, this is going to be 2 minus t plus 6. That'll be 8 minus t. And t is from 6 to 8. Let's go and take a look at another example. Here the given curve is an ellipse given by this equation here. X squared divided by 9 plus y squared divided by 4 equals 1. So to parameterize this one, we're actually going to use a trig identity. We know that cosine squared t plus sine squared t is equal to 1. Then, using the given equation, if we let x equal 3 cosine t, this would give us 9 cosine squared t divided by 9. And if we let y equal 2 sine t, this would give us 4 sine squared divided by 4. That would satisfy the equation for this curve. Now we have both x and y expressed as functions of t. And if we trace out this curve starting here and going around the ellipse, we could let our vector valued function have an x component of 3 cosine t and a y component of 2 sine t for the given curve where t is on the closed interval from 0 to 2 pi. We should be all the way around the ellipse. Let's go and take a look at one more. So for our last example, we have a path that starts here at the origin, follows the cubic function out to this point of intersection, and then down back to the origin along the line y equals 4x. This point of intersection here is the point 2, 8. So this would be curve 1 and this would be curve 2. For curve 1, we can let x equal t. So t would have to be on the interval from 0 to 2. And then if x is equal to t, y would be equal to t cubed. Now for the second curve, we know that t has to start at the value of 2. And our path is along this line from the point 2, 8 back to the origin, or 0, 0. So for x, it starts at 2, and then t also starts at 2, so we have 2 minus and then t minus 2. When t is 2, this would be 0. When t is 3, this would be 2 minus 1. When t is 4, we'd have 2 minus 2, which would be 0, back at the origin for the x-coordinate. Now see if we can find an equation for y. We know the y-coordinate will start at 8 and decrease to 0 along the line y equals 4x. So this slope here is going to be an important part to this equation. We'll let y start at 8, and we want to subtract 4 times. Now if we can come up with an expression in terms of t, where t is on this interval, but this quantity takes on the values from 0 to 2, it would satisfy the values for y. So if we put t minus 2 here, let's check it. When t is 2, we would be subtracting 0 from 8. When t is 3, we'd have 8 minus 4. And when t is 4, we'd have 8 minus 4 times 2, which would give us 0. So this works. Let's go ahead and write this as a vector valued function. So the first curve we have x equals t, y equals t cubed. Close interval from 0 to 2 for t. And let's go ahead and simplify our expressions for curve 2. Here we'd have 2 minus t plus 2, that's 4 minus t. And then for the y component we have 8, and this would be plus 8, so that would be 16, and this would be minus 4t. And t is on the closed interval from 2 to 4. So as you can see, some of these formulas can be a little tricky when trying to determine how to manipulate an expression for t to get the values that we do need to make these formulas work. I hope you found these examples helpful.